Homework 2, problem 4. Find the force between two parallel infinite line charges. To do that, we're going to first find the electric field due to one line charge and then find the force on the other line charge due to that first electric field. We're going to use Gauss's law to find the electric field. The Gaussian surface we will want for infinite line charge is, of course, a Gaussian cylinder that is drawn around the line charge. And so that's going to be something like this. And in this condition, the distance from the center of this Gaussian cylinder to the edge is going to be the same distance d, and it's in the s direction, where s is the radial direction in cylindrical coordinates. So, using Gauss's law, we write down the integral form of Gauss's law, which is the flux of the electric field we want to remember to stick epsilon naught in there, is going to be equal to the volume integral of the charge density. In our case, we can argue through symmetry, right, that the electric field is going to be a function only of the s coordinate in the s hat direction. And the n hat is either on the surface, the n hat is going to be in the plus or minus z hat direction, and on the edge, the n hat, of course, is going to be in the s hat direction. So whenever we evaluate the flux through the end caps is going to be equal to 0. So writing that down, this flux over the closed surface, d2x, n hat dot epsilon naught e, can be broken apart into the flux d2x, n hat dot epsilon naught e through the end caps, and the flux d2x, n hat dot epsilon naught e through the sides. Having z hat dot s hat, of course, is going to give 0, so that term will have no flux, so it all comes from the sides. S hat dot s hat, of course, gives 1, and we know it's going to be constant over the surface, so I just now need the surface area. If I say that my Gaussian cylinder has a length L, this is going to give me the left-hand side of integral form of Gauss's law is going to give me 2 pi little l times d times epsilon naught, the electric field in the s direction at s equals d. Then I have to find the total charge included in that cylinder. Now this is a line charge with line charge lambda, so if I multiply line charge lambda times L, that's the total charge included. So this is simply lambda times L. Divide everything out to solve for the electric field. This is, of course, lambda over 2 pi epsilon naught d. So recovering the vector form of the electric field is going to be lambda over 2 pi epsilon naught s hat, where s and s hat are in the cylindrical coordinates. Now the second step for this problem is to then find the force on the second charge due to this first charge. The differential form that we're going to use, or the integral form that we're going to use to find the force on an extended charge, is still from Lorentz force, but now it's going to be the integral d3x of rho is a function of r times the electric field is a function of r. This is essentially still QE, so the force is still QE, but now it's this d3x rho is going to be the Q that we're looking at, and we have to integrate this over the surface. Inside any volume of length L, what we're going to find for this, of course, is lambda times L. So the force is going to be lambda times L times this electric field that we found here. ES, or ES is a function of D. Divide both sides by the length, and we're going to find that the force per unit length is going to be equal to lambda squared over 2 pi epsilon naught D times S hat, or it's going to point away. The lines will be repelled from each other.